Now it's recording. All right, here we go. So we're at example 5, rewriting before integrating. So there's a couple things we could do here. Is I could rewrite this as x plus 1 over x to the 1 half. Now, there is no quotient or product rule for integrals, okay? There's no quotient or product rule for integration. But what I can do is I can break this apart. And then we do have, remember, the integral of f of x plus d of x, or f of x plus g of x, you can do them separately. And then watch, isn't this x to the 1 half plus x to the negative 1 half dx? Think about that. You would be doing your exponent property. 1 minus 1 half is 1 half, and this just comes up to x to the negative 1 half. Then I can do the power rule. Do you guys see what I did? I broke it apart.
Wait, I have a question.
Yes.
Can't you add those together?
Add.
Not like exponent.
They're not like terms. If it had been x to the 1 half plus 3x to the 1 half, yes, that's 4x to the 1 half. But these are not like exponents. All right. So now I increase the power by 1 and divide by that power. I increase the power by 1 and divide by that power. And it's not very pretty, but that's my answer. My note there says you may not integrate the numerator and denominator separately. That there is no such quotient rule. All right, example 6. Rewriting before integrating. Okay. This is where you're going to have to really know your integrals and what you can do with trig. So I'm going to break this apart, sine x over cosine squared x, as sine x over cosine x times 1 over cosine x. And isn't that tangent x secant x? And I happen to remember that the derivative of something gives me tangent x secant x. What is it?
Secant x.
Secant x, good job. So this is just secant x plus c. So sometimes you're going to have to do trig manipulation to get there.
How about trig?
Okay. All right. You have already seen that the equation y equals the integral of f of x dx has many solutions, each differing from the others by a constant. This means that the graphs of any two antiderivatives of f are just vertical translations of each other. In many applications of integration, you are given enough information to determine what's called a particular solution. Because right now we've been doing general solutions. To do this, you need only know the value of y equals the antiderivative of x for one value of x. This is often called an initial condition. And this is going to be a huge concept. It's usually one of the 6 free response questions. So we will tackle this and be solid on this by May 7th. All right, if we're given dy dx equals 3x squared minus 1, then if you did the antiderivative, that would give you x cubed minus x plus c, right? If you did the integral. It says if we know that the curve of capital F of x crosses or passes through the point 2, 4, then guess what? This is the y value. Here's the x value. And then the only thing that we don't know is c. So if you're given this initial value, you can then figure out exactly what the c is.
It's like you're finding b.
Yeah. So c is -2. So here's what's called the particular solution. Alright, we're going to do another one. It says find the general solution of f prime of x equals 1 over x squared, and find the particular solution that satisfies the initial condition f of 1 equals 0. So remember, if we want to find f of x, to undo the derivative, you have to do the integral. So this is the integral of x to the -2 dx. So we increase the power by 1, divide by the new power, and add that constant of integration. So f of x is actually -1 over x plus c. Now we're going to use the initial condition, 1, 0, to find out what the constant of integration is.
Mrs. McInerney.
Yes.
If it's something simple like 1 over x squared, can we just, like if we don't have to do the summation to get the answer, like we can do it in our head?
Absolutely,
We can
absolutely.
skip this
Yeah.
summation.
So I'm going to get 0 equals -1 over 1 plus c. Yeah, I'm just trying to put all the steps in for anybody who needs to see it.
I feel like you're lying to us. And I really can't do this easy. I know this is really, really, really easy.
Are you guys for real?
No.
Yeah, it's not.
It is.
It's
This
not
is
that
No.
hard.
easy.
I'm gonna fail the exam, especially this part.
Wow, that's wonderful to hear. Not what Sam said. Sorry, that came out wrong.
This is recorded.
I'm so sorry.
See how
This
she is,
recorded.
Jackie?
I meant what you guys were
Now
saying
we'll
was
really
so
know
easy.
if she
That was
actually
really
looked it
recorded.
up.
Yeah.
We'll really know.
Okay. Alright, so note, we have used x as the variable of integration. It is possible to use different variables.
We have.
And we actually did this a little bit earlier, so maybe that's why you're thinking it doesn't seem that bad. Let's look at example 8. It says, a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function giving height s as a function of the time t. So something you need to remember is that velocity equals the derivative of the position function, and acceleration is either the derivative of velocity or the second derivative of position. Okay, that's something you're supposed to remember. So a ball is thrown upward with an initial velocity of 64 feet per second. So they're telling me the initial velocity is 64, the initial height is 80. So that's information that they're giving us. And since it's in feet, you guys remember from your physics class that gravity is -32 feet per second squared?
No. I'm not in
Something that's supposed to be common knowledge is that gravity is -32 feet per second squared.
We do it in meters
Yeah.
twice.
Oh,
It's
okay.
like
Is it
9.8
9.8 or
Yeah.
something like that? Okay. Well, in your homework, it's kind of, they don't come out and tell you this, so let's try to remember it. And so that's the acceleration due to gravity. But that is also the second derivative of position. So if I can take the integral of the acceleration, you remember that that's going to give me velocity? The integral of acceleration will produce velocity. So all I have is that it's -32 dt. So that's -32t plus c is going to give me velocity. but they gave me the initial velocity. So if I let t be 0, what would c be?
Yeah. 32t.
Yeah, so c is just 64. So I now have an equation for the velocity is negative 32t plus 64. Unfortunately, I don't need that right now. To get position is the integral of velocity. So this is going to be the integral of negative 32t plus 64. So what I want you to notice is we keep using initial conditions here. So this is going to give me negative 16t squared plus 64t plus c. Now because it was initial position, c is 80. So s of t is negative 16t squared plus 64t plus 80. So that's the position function. That's the answer for letter A. So let me go back through it again to make sure we understand. You've got to bring to the problem a few things. You need to understand that velocity is the derivative of the position function, and that acceleration is the derivative of velocity or the second derivative of the position function. So it's like you're going to work backwards. You're going forwards and backwards here. And knowing that acceleration due to gravity is your negative 32 feet per second squared. And then we just integrated twice. Now, when does the ball hit the ground? That's not calculus. When does the ball hit the ground? What do you know? For the ball to hit the ground. The height is 0, right? When it hits the ground, the height is 0. So that's what I think can be so tricky about physics, is that there are some of these things that you have to infer. They don't come out and say, oh, the height is 0 at the ground. They're saying, okay, when does it hit the ground? Well, you've got to know what's the height. It's 0. What I would suggest you do is bring everything over to the other side and make that squared term coefficient positive. And then I think 16 will go in there evenly. That's a 4, sorry. You could even just divide by 16 because it's an equation. So you're getting t is 5 or t is negative 1. Well, you can't have negative time. So it's 5 seconds.